All right, so we're going to hit pause on our discussion of normal variables and talk about linear correlation. And at first glance, it might seem like, why are we taking this strange detour? The truth is that this section, this chapter, chapter 4 stuff, is really kind of an oddball chapter. It doesn't really fit in with a lot of the other material that we cover in the class. It's good information, it's good material, and it's important statistics, but it's just kind of hard to fit it in with anything else. But I like to cover chapter 4 at this point in the course because what we discussed in 7.1 and 7.2 is that if you know that a variable is normally distributed, then you can use the normal calculator in StatCrunch to compute probabilities involving that variable. But the question is, how do you know if that variable really is normally distributed? And the way that we determine the answer to that question is very similar to the way that we determine if there's a linear correlation between two variables. And that's the topic of discussion in chapter 4. So that's why we're going to cover this now. So let's do it. So just as a reminder, because it's been a while since we've talked about response and explanatory variables, the response variable, or in other words, the dependent variable, is the effect. You can think of that like the effect, and the explanatory or independent variable is the cause. So if you're thinking about cause and effect relationships, then the explanatory variable is the cause and the response variable is the effect. Okay? Now, the first step in determining whether a correlation exists between two variables is to plot the data on a scatter diagram, or scatter plot is another word for it. In a scatter plot, each individual is represented by a point. The explanatory variable, so the explanatory variable is plotted on the x-axis, and the response variable is plotted on the y-axis. And it's not always clear which variable is going to be the explanatory variable and which variable is going to be the response variable. Like if you just notice that there's a correlation between two variables, it's not always clear which one's causing the other. And in fact, it may not even be the case that either of them is causing the other to happen, right? But most of the time it's clear from the scenario which variable the researcher believes to be the explanatory and which one they believe to be the response. And so it'll be pretty clear when you're working through the homework problems which one is which. So for example, this first one says, construct a scatter plot for the data obtained in a study of the number of absences in the final grade of 7 randomly selected students from a statistics course. This is completely made up, by the way, so don't worry. If you missed class 15 times, you should definitely fail. Well, that's not true. I mean, it's okay to miss class if you still understand the material, but apparently this student did not. And honestly, it's been my experience that students who miss a lot of class don't pass the class. It's like this fairy tale that students like to believe that, like, oh, college, I can just like not go to class. And yeah, that's true. You can not go to class, but you're going to fail the class most likely if you don't. Anyway, so construct a scatter plot. Well, so the absences are going to go along the x-axis, right? The final grade is going to go along the y-axis. I need to go all the way out to 15 along the x-axis, and then along the y-axis, it looks like I need to go all the way up to 90, but the smallest value is 43, so I'm probably not going to start right at 0. But let's go ahead and draw our axis system. So on my x-axis, well, and then in my y-axis, I'm not going to start right at 0, so I'll put this little symbol in here to show that, I'm not starting right at 0. I'm going to start at, maybe I'll start at 40, right? So I'll start at 40, and then go up in increments of 5, so 40, 45, 50, 55. Well, I'm going to run out of room. 40, 45, 50, 55, 60, 65, 70, 75. Ooh, I better come back and have them. So 40, 45, 50, 55, 60, 65, 70, 75, 80, 85, 90. So 90 is right there. Not my best graph that I've ever made. That's okay. And then along the x-axis, I'll have the number of absences. So the smallest number was 2, the largest number was 15. So I think I'll go 2, 4, 6, 8, 10, 12, 14, 16. That was a little better. So this is the absences, and this is the final grade. And to title the scatter plot, we could call it something like absences and final grades, or something like that. You could probably come up with a better title than that, but anyway. So now what we're going to do is we're just going to treat each of these observations as an ordered pair, right? So we're going to plot the point 682, right? 682, something like that, and then 286, and so forth. So I'm going to stop talking and just plot points. Okay, my daughter has snuck in to ask me a question. But anyway, this is the scatter plot that we come up with. So you should come up with something like that, more or less. Okay, so
can I ride my scooter?
Yes, you can ride your scooter. Oh my goodness. Okay, so sorry. Okay, so there's our scatter plot, right? Now, if you look at the scatter plot, these points look more or less kind of like on a straight line, right? And when the points lie on more or less a straight line, we say that there's a linear correlation between the variables absences and grade in this case, right? So a linear correlation is one in which the scatter diagram forms a straight line, more or less. Two linearly correlated variables are positively associated if y increases as x increases, and they're negatively associated if y decreases as x increases. In other words, if you imagine reading the graph from left to right, right? So x is increasing when you move from left to right. If you're falling as you move from left to right, then that's a negative correlation. If you're rising as you move from left to right, then that's a positive correlation. So in this case, I'd say we probably have a negative correlation, right? So number 2 says, do the variables from example 1 have a linear correlation? It seems so. And if so, are they positively or negatively associated? Yeah, it seems that there's a negative linear correlation between absences and final grade. Another way to think about the whole negative positive thing is that, like, obviously absences are going to have a negative effect on your final grade, right? Like, they're going to drag down your final grade. So that's why there's a negative correlation between those variables. Okay? Now, it's not always easy to tell just by looking at the scatter plot whether or not there's a linear correlation. And so we have a mathematical way to determine if there's a correlation, and it's to compute this thing right here called the linear correlation coefficient. As you can see, this is a gnarly calculation. Just appreciate this with me for a second, right? So S sub x and S sub y denote the standard deviations of the x and y variables. X bar and y bar are the means of the x and y variables. So it's like you have to compute, in order to compute this correlation coefficient, first you have to compute 2 standard deviations, a couple of means, and then you have to compute, and then if you look at this just right, if you squint at it, this is a z-score for the x, this is the set of all the z-scores for the x variable, This is the set of all the z-scores for the y variable. So you calculate the z-scores, multiply them together, add them up, right, and then divide by n. It's just, this is a long and tedious process. So we're not going to be doing this on our own. We're going to let StatCrunch do the heavy lifting. Okay, so we're not going to do this calculation by hand, but it is important for us to be able to interpret it. So here's the interpretation. First of all, r is always going to be between -1 and +1. If r is close to +1, then there's a strong positive linear relationship between the variables. If r is close to -1, then there's a strong negative linear relationship between the variables. If r is close to 0, then a linear relationship does not exist. Now that doesn't mean that there is no relationship between the variables, it just means that there's no linear relationship. And so here's some possibilities. These charts come from your book, but here you have like a perfect linear relationship. Here you have a strong linear relationship, it's not perfect. Right? Here you have kind of a moderate linear relationship, and these are all positive relationships, right? Because you're rising, the graph is rising as you move from left to right, okay? So those are positive. And here you have a perfect negative linear relationship, a strong but not perfect negative linear relationship, a moderate negative linear relationship, okay? And then here you have no linear relationship at all. Actually, this shows that there's no relationship whatsoever, right? The dots are just all over the place, and so r is close to 0. But for a graph like this, there's clearly a relationship between the variables, okay? But it's not a linear relationship. And so for this kind of graph, r would still be close to 0. So just by looking at the correlation coefficient r, if you get an r value that's close to 0, you really don't know which of these scenarios you're looking at. If you go on and take more statistics courses, then you'll talk about other kinds of linear, other kinds of regression analysis, in which you look at correlations of nonlinear types like this. But if we're testing for linear correlation, then both of these show no linear correlation, even though this one shows a correlation, but it's just not linear, okay? So in both of these cases, r is going to be close to 0. Now, as I said, we're not going to do these gnarly calculations by hand, so we'll let StatCrunch do the heavy lifting. And by the way, if we want to make a scatter plot in StatCrunch, we can do that by going to graph and then scatter plot. The correlation coefficient can be found under stat, summary stats, correlation. There's another way to get the correlation coefficient as well that we'll talk about in the next section. Okay, but for now, this will give us the correlation coefficient we're looking for. So let's practice. Okay, so example 3 here says, compute the linear correlation coefficient r for the data in example 1. Example 1, so that was this example right here, absences in final grades. So let's do that. We're gonna have to go to StatCrunch, and I've taken the liberty to go ahead and put the data into StatCrunch already. So this is that first example that we're looking at. You should follow along with me, so go ahead and give the video a pause and enter the data into StatCrunch so that you can follow along with what I'm doing. But I'm gonna go ahead and move forward with this, right? So here's the data. Now, if I want to compute the correlation coefficient, then I'm gonna go to stat. Well, actually, let me show you a scatter plot as well. So if I want to make a scatter plot, I would go to graph and then scatter plot. Okay, and then you have to tell StatCrunch which one is your x variable, which one's your y. So we want the number of absences to predict the final grade. And then you hit compute, and it gives you that scatter plot, which looks more or less like the one that we came up with. So that's pretty nice. And now the correlation coefficient. So for the correlation coefficient, you go to stat, summary stats, correlation. We want to see if there's a correlation between absences and grade. So we'll click on that. Oh, maybe let me just do that again for you. So it's stat, summary stats, correlation. I want to see if these two variables are correlated. So what I'm doing is I'm just clicking and dragging, right? Like if I try to click this one and then I try to click this one, it won't highlight both of them. And you need both of them to be highlighted. So if you just click and drag, then it'll highlight both. The other thing you could do is to hold down Control on your keyboard. You click and then hold Control and then click again, then it gets both of them in there. Anyway, hit compute, and there's your correlation coefficient, negative 0.944. Okay, so I'm going to go back and write that down. So we usually round these to 3 decimal places. So let's say R is about negative 0.944. Okay, so that's how we get a correlation coefficient. Now, we still kind of have to answer the question, okay, so you get this correlation coefficient. Let's say the correlation coefficient is like 0.7. Is that good enough to say that there's a linear relationship between the variables? Well, that depends. It depends on how much data we have, right? So note that the fewer the data points, the more likely there's a linear relationship between the variables, right? So like if there are only 2 data points, then of course there's a straight line that goes between the 2 points, right? There's always going to be a straight line between 2 points, right? If on the other hand there are 50 data points, then it might be harder to see a linear correlation, right? So exactly how close to 1 or negative 1 does R have to be in order for us to conclude that there's a linear correlation? Well, what we're going to do is we'll use a table of critical values, and these critical values are going to serve as cutoff points to tell us how good our correlation coefficient needs to be. So I should label this as absolute value of R. So what we have here is the number of data points, right, our sample size, and then here we have the critical value, or maybe a better label for this, instead of calling it absolute value of R, maybe I'll call it CV for critical value. Okay, so what this means is that if we only have 3 data values, then our correlation coefficient needs to be bigger than this critical value, 0.997. If we have 13 data values, then our critical value needs to be bigger than 0.553. Okay, so that's how this chart works. This chart comes from your book, by the way. You can find it in your book, or you can just refer back to this chart in your notes when you need it. So to use this table to figure out if there's a linear correlation, here are the steps that we take. First of all, we'll use StatCrunch to compute the linear correlation coefficient. Then second of all, we'll take the absolute value of that number. And then third, we're going to use the chart to find the critical value that corresponds to the number of data points that we have to work with. If the absolute value of our correlation coefficient is bigger than the critical value, then we conclude that there is a linear correlation. Okay, so for example, let's say that we have 12 data points and that the linear correlation coefficient, we use StatCrunch to calculate that, and we get a linear correlation of 0.521. Okay, well, so then the absolute value of 0.521 is again 0.521, and since n is 12, the critical value is 0.576, right? So this is the number that we have to beat, right? Our correlation coefficient needs to be bigger than this, and it's not, right? Right, the critical value is 0.576. Can we conclude there's a linear relation between the variables? Well, we would say since absolute value of R is less than the critical value, right? The absolute value of R was 0.521. The critical value is 0.576, right? So since the absolute value of R is less than the critical value, there is not a linear correlation. Okay, so that's how that would work. So using our previous example, right, we already computed the linear correlation coefficient for the data in example 1. It was about negative 0.944. Based on that can we say that there's a strong linear correlation between the variables? And is it positive? Is it a positive or negative correlation? Well, let's see. So absolute value of R would be about 0.944. And the critical value, well, let's see. For the critical value, for the data in example 1, we had, I think, 7 observations, right? 1, 2, 3, 4, 5, 6, and 7. So we had 7 observations. So n equals 7. For n equals 7, the critical value is 0.754. Okay, so the critical value is 0.754. So that's the number that we have to beat. Our correlation coefficient needs to be bigger than this in order for us to conclude that there's a linear correlation coefficient. And it is, right? 0.944 is bigger than the critical value. So I would say since absolute value of R is greater than the critical value, what critical value, right? In other words, 0.944 is greater than 0.754, right? So since absolute value of R is greater than the critical value, there is a linear correlation. And then, is it positive or negative? Well, since R is negative, the correlation is negative. Right? So there is a strong negative linear correlation between the variables in example 1, which, if I remember correctly, are grade and number of absences, right? So there's a negative linear correlation between grade and number of absences, which aligns very nicely with what it looks like should be the case, right? It looks like there's a negative linear correlation between those two variables. Okay. So let me give you one more example. This time we'll just work this example from beginning to end without any interruptions, hopefully, unless my kids break into the room, which is very possible to happen. Anyway, but let's see. It says the data below describes the monthly income of 7 people and the number of times they eat out each month. Is it 7 people? 1, 2, 3, 4, 5, 6, 7, 8. It's 8 people. It's 8 people. I can't count apparently, but we've got 8 people here. It says use StatCrunch to do the following. So draw a scatter plot, find the correlation coefficient, and then answer the last question: what type of linear correlation, if any, is there between income and meals eaten away from home? Well, let's see. So for part A, we're going to do this in StatCrunch. We're just going to go to we're going to go to graph and then scatter plot. And then we'll just look at the graph. I'm not going to redraw it on the page. We'll just look at the graph. But then for the correlation coefficient, we're going to go to stat, summary stats, and correlation. And we'll see if there's a, we'll see what the linear correlation coefficient is. So let's do those things. Again, I've already entered the data into StatCrunch here. So if you haven't done so already, go ahead and pause the video and enter the data so that you can follow along with what I'm doing. So if I want to get a scatter plot, then I go graph, graph, scatter plot. I always have a hard time seeing it for some reason. There's the scatter plot. Income and meals, that's what I want to compare. Ooh, so there's the scatter plot. I don't know. It kind of seems like maybe there's a vague linear correlation. But then again, look at this dot over here, right? So I don't know. It kind of seems like the dots are all over the page to me. My guess is that probably there's not a linear correlation here. But let's see. We go stat, summary stats, correlation. And I want to see if income and meals are linearly correlated. So I hit compute. There's the correlation coefficient, negative 0.297. So let's write that down. Okay. And then part C asks, what type of linear correlation is there between income and meals eaten away from home? Well, first of all, we know that the absolute value of R is going to be about positive 0.297. And second of all, the critical value for n equals 8. So for eight observations, the critical value is 0.707. 707. And this is for n equals 8, right? N equals 8 here. Okay. Well, so based on that, right? This is my cutoff value, right? My correlation coefficient needs to be bigger than this in order for me to conclude that there's a linear relationship. And it is not, right? It's not. So we'd say since 0.297 is less than 0.707, right? In other words, this is absolute value of R, this is your critical value. Since the correlation coefficient is less than the critical value, there is no linear correlation. Okay, so that's that. That's how these examples are going to work out in this section. One thing that I want to talk about that we've mentioned in this course already, but that I want to rehash here because this is a very important concept that you should walk away from statistics understanding thoroughly. And it is this, that correlation does not necessarily imply causation. So even if you determine that two variables have a correlation, that there's a correlation between the two variables, that doesn't necessarily mean that that there's a causal relationship between the variables. It doesn't mean that one of them is causing the other to happen. So for example, teenage birth rates and homicide rates have both been declining since 1993. So there's a correlation between those two variables, right? That doesn't mean that either of them has to do with the other, right? It's not like teenagers are more likely to use birth control or something because people are killing each other less, right? Like there's no relationship there between those two variables, right? One of them isn't causing the other one to happen. There could be a third variable that explains the decline in both of these, but that doesn't mean that this one is causing that one or that this one is causing that one. What's happening in that situation is that this third variable is causing them both to decrease. Right? And so maybe a variable like that exists where there is a causal relationship, but that's not the case here. Just because there's a correlation doesn't mean there's a causal relationship. Another good example of this is the idea that kids enrolled in music programs have higher GPAs, right? That's a true statement, right? Like there is a correlation between being enrolled in music programs and having a higher GPA. But when I was a kid, and I was enrolled in music programs and stuff, the story that was being told at that time was that learning about music increases your intelligence because you were working out a different portion of your brain, and so it made your brain work better and all this stuff. Well, it turned out that there was actually no evidence to support that. It was just a theory that people had. And they saw this correlation, right? They saw the correlation between kids in music programs and then them having higher GPAs, and they just assumed that it was being enrolled in music programs that caused them to have higher GPAs. But when people actually sat down and tried to figure out if that was true, they found out that there was not a causal relationship between those variables. Most likely what was happening is that the kids who were enrolled in music programs had very supportive parents and stuff who were more likely to like help them with their homework and push them to do really well in school. And so consequently, they had higher GPAs, right? So it's like both of these variables, they didn't have anything to do with each other. What was really happening is that there was a third variable that was causing them both to change, right? And this is the danger when you're dealing with correlation, because it's really tempting when you see a correlation between two things to think that one of them is causing the other to happen. But that's not necessarily the case. And we have to be really careful with that because it can cause some real problems in the world when we assume that causality follows necessarily from correlation. Um, Here's another link to some kind of funny ones. So they do it graphically. So if you're interested, you can click on this link and see some other examples of places where there's correlation between things, but not necessarily causation between the things. And the graphs are pretty funny. Like I think the first one on there is something about divorce rates and consumption of margarine or something like that. Like there's this strange correlation between them, but it's obviously not a causal relationship. So anyway, so there's that. Here's your homework assignment, and we'll see you in 4.2.